All right, hello everyone. This is the follow-up part two, I guess, of section 10.1, chi-squared distribution. So hopefully you can see my little iPad here. So what we've already talked about is how to find a chi-squared test statistic. We've done test statistics for other hypothesis tests. So the idea is we just need a test statistic, and now we have a way to find a test statistic. Now the question becomes, how far away is that test statistic? So in our other problems, we know that anything, let's say, over 1.96 standard deviations away, or a test statistic of more than 1.96 is going to cause us to reject the null hypothesis. But a chi-square distribution looks different than a normal distribution. So first things first, the chi-square distribution is always skewed right because the smallest number you can ever have, the perfect distribution would be zero, right? Or not perfect, but if you got everything you expect to get, you'd have zero, and then just positive numbers. So our chi-square distributions tend to look like this: smaller numbers than skewed right. So the question becomes, where's our cutoff, right? Here's our 5%. So first of all, we'll always have just one tail. It's always on the right. Here's our 5%, right? So how far is that cutoff? We were playing around with our test statistic of 2.6. And in class, we try to find p-values of that and that kind of stuff. But now we're going to just generally talk about what's the cutoff. Okay. So first of all, we have the more categories, the less skewed this distribution becomes. So we did one with 6 categories. If you could do it with 4 or 6 or 8 or whatever. The more categories, the less skewed the distribution is. So the cutoff will change. So we have this thing called degrees of freedom, just like we did for a t distribution. So the degrees of freedom here is the number of categories minus 1. So like our other problems, we have a chart that's going to help us find these cutoffs. Normally we would do like an inverse norm. If we were doing normal, we'd do an inverse norm to find these cutoffs, right? So we'd love to have an inverse chi-squared button, but there is no inverse chi-squared button on the calculator. So we're going to have to use our chart to find these numbers. So I'm going to flip over to the chart here in just a second. It's also in the back of the book. It's on your note sheet. But just to remember, we're looking, our cutoff could be anything. It could be 1%, 5%, 10%. So I'm going to go with the 5% for right now. We'll do our problem, which had 5 degrees of freedom, right? So the number of categories minus 1, 6 minus 1. So we want this cutoff. So once we have that cutoff, we can then run a test. So let me jump over to my note sheet here, just so you can see it. It's also in the back of your book. Here's the chi-squared distribution. Notice just right tail. Okay, just right tail. So you just want to use that probability. We wanted a 5% right now. We could do anything. So here's my 5% tail probability. Right. So we go 5%. We also had 5 degrees of freedom, 5%. There's my cutoff for how big the test statistic can be before it becomes not reasonably likely. Okay, so you can look up any numbers in this chart, not any, but you can see the cutoffs: 25, 20, 15, 10, 5. Okay, and then the degrees of freedom. So we're going to go back to our problem now. Give me 1 second here. And I will erase my little writing here, and you'll see that the cutoff actually 11.08. Okay, so let's talk about how to run a test now and how it all sounds together and everything like that, right? So this is called a chi-square goodness of fit test. We have a distribution that we think is supposed to happen. In the case of the dice problem, we expect 10, 10, 10, 10, 10, 10, whatever the case is. It could be anything, any guess for any distribution. And then we would take a sample and compare it, right? So it's called a chi-square goodness of fit test. How does your data fit your model? So there are some conditions. So here are the conditions. First condition is each outcome must fall into exactly one of a fixed number of categories. You can't have outcomes that are in 2 different categories. Okay. You can model your hypothesized proportions. This is a little bit silly, but we have to have a model, which we're going to have. It has to be a simple random sample. Sorry, I guess I should say SRS here. And then maybe the most important one is each expected outcome, each E or expected outcome has to be greater than or equal to 5. It's the whole same idea. We need to get enough to make our distribution look like it's supposed to look like. So each expected value is greater than 5. And as normal, you would not just say that, you would confirm it. And I'm going to run an entire test here in just a second after I go through a general one. Okay. So we're going to state our hypothesis. The null hypothesis is just going to be whatever our model is. So for like the dice problem, we would say, I expect 10 ones, 10 twos, 10 threes, 10 fours, 10 fives, 10 sixes. Okay. Or you could write that in a set. You could just say 10, 10, 10, 10, 10. This is my model. There's lots of different ways to do it. You'll see me do one here in just a second. The alternate would be our model's no good, right? Or at least one of the proportions is not equal to the model. So we're going to make a judgment. If we reject the null hypothesis, we're going to say there's evidence my model is wrong. If we don't reject it, we're going to say there's no evidence the model is wrong, just like we've done in the past. We can compute the test statistic, find a p-value, draw a sketch, just like we've done for every other problem, right? So there's that chi-squared test statistic again. It's observed minus expected squared over expected. Okay. The degrees of freedom is the number of categories minus 1. And at the end, we're going to write a conclusion in context. So I'm going to do an example, degrees of freedom there, sorry. But everything kind of works the same as we've done before. Okay. So here's our question. Is the proportion of peanut M&Ms the same as plain M&Ms? All right. So in the plain M&Ms, we had 20% red, 20% yellow, 10% green, 10% orange, 30% brown, 10% blue. And then we take a sample of the peanut ones, and we're going to see if the model shows us whether we think they're in the same proportion. All right, so let me walk you through the steps here. So step number 1, just like before, is name the test. So chi-squared goodness of fit test. Make sure we meet the conditions. So we'll just tell us it's a simple random sample here. Second condition is we can model. And there's our model, right there. The third condition is each outcome, and you can just say these ones, each outcome falls into one category. And then the last one is the big one, right, is each expected value greater than 5. So we're going to show that. I think we can say greater than or equal to is okay. So we're going to show those. So what we have here is let me get out my calculator here. We took a sample of 11 plus 16 plus 8 plus 5 plus 17 plus 18. So we took a sample of 75 peanut M&Ms, right? And we expected 20% red, 20% yellow, and so on. So we need to know what those numbers are. Those are my expected values. And they're also very important anyway because I need them to run the test, right? So let's write them out. So the expected would be 20% of 75, which is 15 for the red. I'll just put a little color. Yellow is 20%, so 15. Green is 10%, so 7.5. Orange is 10%, so 7.5. Brown is 30%, which would be 22.5. And blue is the 10%, so 7.5. So all greater than or equal to 5, check, we've met our conditions. We need those expected values anyway, so it's not really extra work, right? Those all came from the percents that I expected out of the 75. My null hypothesis would be something that peanut M&Ms match model of plain. You could say it that way. You could also just say, because I know other problems will just have our percents or our model that we think. So we could say, or the model is 15. Let's do it with percents because this is precise. Sorry, 20% red, 20% yellow, and so on. I'm not going to write it all out right now just to save us a little time on our video, but you would just write out the model. The alternate is model is wrong or not what we expect. Or sorry, I shouldn't say it that way. So yeah, we'll just say model is wrong. That's kind of general. So I might say that the peanut M&Ms do not match the plain M&Ms, or the model is not 20%, not 20%, 20%, so on. Okay. So I'm going to draw a picture. It's a chi-square distribution. We had 1, 2, 3, 4, 5, 6 categories. So our cutoff, we need our cutoff here. It's the same cutoff as it was for the dice, right? 6 categories. Sorry, that was probably a bad example of the same. So I think that cutoff was 11.8, so at 08, so I don't have to look it back up. My chi-square test statistic, you can just do this work on your calculator. The easiest way is to do it in list, but you can also just do observed minus expected squared over expected for each one, so on. You can also put list 1 as your observed, list 2 as your expected. Sorry, I can't show you my calculator right now, but you could put list 1 as observed, list 2 as expected, and then you could do your list 3. Remember, you could just do observed minus expected squared over expected. So you can do list 1 minus list 2 squared over list 2. And then just add up that list 3. So sorry, I'm going to just kind of do this. I probably should have done this in advance, but I wasn't prepared. I apologize. So I'm just going to kind of walk you through what I'm doing right now. I'm just on my calculator. I'm on my list. So my list 1 is going to be my observed. Okay, so 11, 16, 8, 5, 17, and 18. My list 2 are going to be my expected, which are 15, 15, 7.5, 7.5, 22.5, and 7.5. And now I'm going to move over to list 3. And up at the top, remember I have my cursor up at the top, I'm going to do observed minus expected squared over expected. So I'm going to go in parentheses just to protect myself, observed minus expected. So list 1 are my observed minus my list 2, which are my expected, squared. Okay. Remember the chi-squared test statistic? I got written down here somewhere. Where did it go? There it is. Observed minus expected squared over expected, right? So now I got to divide it by my expected, which is my list 2. Now I have all those numbers. I just want to add them up. So I'm just going to go to stat, calculate one variable statistics on list 3, add them all up, and that's my number, which is 18.04. It's in the rejection region. I'm going to find a p-value. So we're going to do p-value the same way we've done p-value before. Normally we do normal CDF, right? But this time it's going to be chi-squared CDF. There's a chi-squared CDF button on your calculator. All right, so we're going to go distribution. It's down below. It's number 8 on my calculator, chi-squared CDF. It needs the lower bound, which is our cutoff 18.04. So remember, we're kind of just trying to find this area right here, right? So my lower bound is 18.04. My upper bound is just infinity. And then it also needs the degrees of freedom. So the degrees of freedom is 5. So we get a p-value of 0.29%. Sorry, I should write this in here. 18.4 infinity with 5 degrees of freedom. It's 0.29%. Very small, right? We're going to reject the null hypothesis. So there is evidence that our model is wrong, or there's evidence that peanut M&M proportions, be specific to the context of the problem, right? Peanut M&M proportion is different than the plan. So there's kind of a walkthrough of a chi-squared goodness of fit test. Usually the trickiest thing is just trying to get the null hypothesis, believe it or not, the model. It's kind of weird to write sometimes. So you can have some homework on that, and then we'll go over some questions in class.